The world is strange. The whole universe is very strange. But when you look at the details, the rules of the game are very simple. One of physics' greatest minds, Richard Feynman, once compared deciphering the laws of reality to watching the gods play chess. Except in this case, you're only allowed to watch snippets of the match and can often only view a tiny corner of the board. From these scant clues and snatched glimpses, you have to work out the rules behind the movements of the pieces, and instead of rooks, knights and pawns, you must attempt to decipher the laws governing fundamental particles, such as electrons, photons, and quarks. Sometimes these investigations bring forth great revelations. At first, you may notice that a bishop always stays on the same coloured squares. Watch for long enough, though, and you'll discover that, while true, there is an even more fundamental rule at play. Bishops can only move diagonally, which in turn explains why they always stay on the same coloured squares. The history of understanding our world is littered with similar revelations. Often, two sets of rules are suddenly married together into one. What looked complex instantly gets simpler. Two apparently separate forces revealed to be actually two sides of the same coin. Two particles, just equal and opposite vibrations, the yin to each other's yang. But the path to this point has been an arduous one. Every time physicists have thought they were getting close to understanding all the rules, they have spotted some tiny hole in their theory that they can't explain. It's the equivalent of one of the special moves in chess, castling. This is when the king moves more than one space and swaps order with the rook. Castling simultaneously breaks 3 of the normal rules of chess, and yet can be a very powerful move, a decisive move, in any match. As Feynman said, it's the thing that doesn't fit that's most interesting. It has to do with curiosity. It has to do with people wondering what makes something do something. What we are looking for is how everything works. What makes everything work? This long and winding road has delivered modern physicists to the precipice of a remarkable breakthrough. We might not need an endless list of ever more complicated rules. Instead, it is possible that all phenomena in the known universe, from the tiniest subatomic particles to all the fundamental forces, and so, by extension even ourselves, can be explained using just one rule. That almost everything is simply vibrations in a vast web of quantum fields. But is this really the end of the game? Or are there still quirks in the rulebook, lurking just out of reach? Thank you to BetterHelp for sponsoring this video. Everything we call real is made of things that cannot be regarded as real. The world of theoretical physics is full of moments that pull the rug from under you, and so is day-to-day life. Sometimes you just need someone to help you organize your thoughts. BetterHelp is the world's largest therapy service, and it's 100% online. With BetterHelp, you can tap into a network of over 30,000 licensed and experienced therapists who can help you with a wide range of issues, whether existential questions like what is everything made of, to more down-to-earth problems. To get started, you just answer a few questions about your needs and preferences. That way, BetterHelp can match you with the right therapist from their network. With BetterHelp, you get the same professionalism and quality you expect from in-office therapy, but with a therapist who is custom-picked for you, with more scheduling flexibility and at a more affordable price. So, get 10% off your first month at betterhelp.com/HOTU, and I've also linked them below in the description. Thanks to BetterHelp for supporting educational content on YouTube. And then to discover, if you try to get answers, that they are related to each other, that things that make the wind make the waves, that the motion of water is like the motion of air is like the motion of sand. The fact that things have common features, it turns out to be more and more universal. What we are looking for is how everything works. What makes everything work. Cities and continents whiz by as the Japanese Hitomi satellite hurtles around the Earth at almost 30,000 kilometers per hour. It is racing so fast it sees 15 sunrises and sunsets each and every day. With a total spend of 300 million and 30 years to build, it was conceived to look at some of the most violent events in the known universe. Yet within weeks of launch, it would meet a violent end of its own. A catastrophic system failure sends it spinning out of control. The team behind the mission try firing onboard thrusters to slow it down, but that only makes Hitomi spin faster. It is now rotating so quickly that its solar panels shear off and the satellite breaks apart into pieces. The mission over, before it is barely begun. But why? What brought down Hitomi? The ensuing investigation discovered that the initial failure occurred as Hitomi passed over the South Atlantic anomaly, a dent in the Earth's magnetic field. This exposed it to higher levels of radiation from space, frying its delicate circuitry. The Earth's magnetism usually acts like a giant bubble, protecting us from the ravages of such radiation. It begins deep in the bowels of the planet as the Earth's molten outer core spins. Surging through the crust and out into space, it spreads its magnetic tendrils out to around 6 million kilometers. The South Atlantic anomaly is caused by a magnetic reversal in a small part of the outer core, and satellites passing through the region are left vulnerable. And so though it may pass by unseen in our daily lives, the magnetism all around us is extremely powerful. Humans have been fascinated with the Earth's magnetism for millennia. The first compasses were made 2,000 years ago during the Han Dynasty in China, when naturally magnetized pieces of iron called lodestones were used for land navigation. Centuries earlier, the ancient Greek philosopher Thales of Miletus thought lodestones had souls because they attracted iron to them. But it took far longer for scientists to explain magnetism, and in doing so, a fascinating new concept crystallized: the field. In physics, a field is a region in which each point has a physical quantity associated with it. Television weather forecasts are a good example because they show how the temperature varies across a given region of the Earth's surface. Those maps are temperature fields. They tell you the temperature you'd experience if you were placed in a particular part of the map. Similarly, the Earth's magnetic field is a map illustrating the strength and direction of the magnetic force a particle would feel at various points around the planet. The South Atlantic anomaly is a part of the map where the Earth's magnetic field is particularly weak. The International Space Station has extra shielding to deal with the increased radiation that lets in, and astronauts aren't allowed to spacewalk while passing through this region. First used by English scientist Michael Faraday in 1846, he saw fields as more than mere mathematical maps. He considered them physical objects that fill otherwise empty space. And to illustrate this, Faraday used this idea to help explain the perplexing behavior of ordinary bar magnets. At some point, every child becomes fascinated with the magic of magnets. Try and push two north poles together and they resist. You can feel them pushing apart from one another. How can they do that without even touching? What's going on in the space between them? Faraday's answer was that the magnets may not be touching, but their magnetic fields are. His explanation introduced the concept of field lines. You may remember the classic school experiment of sprinkling iron filings around a bar magnet, which trace out the magnet's field lines, looping out of the North Pole and back into the South Pole. The magnetic field is strongest at these poles, and so the field lines are packed more tightly together. At least that's the 19th century way of thinking about it. As we will see, the truth is much stranger. Yet that was not the end of Faraday's genius. His most famous discovery came when he found that changing a magnetic field can induce an electric current in a nearby circuit. A decade earlier, the Danish physicist Hans Christian Ørsted had spotted the reverse, that an electric current passing through a wire deflected a nearby compass needle away from magnetic north. Clearly, a changing magnetic field could influence an electric field, and vice versa. Why were the two fields so connected? The answer would come from Scottish physicist James Clerk Maxwell. In 1865, Maxwell describes Faraday and Oersted's discoveries mathematically. This work is so important that in 1999, leading physicists voted Maxwell the third greatest physicist of all time, behind only Einstein and Newton. Maxwell's equations show that rather than being two separate fields, electric fields and magnetic fields are both components of a single electromagnetic field. That's why changing one changes the other. You're altering parts of the same thing. Maxwell had combined two seemingly separate phenomena into one. In the chess game of the gods, spotting that changing magnetic fields and electric fields influence each other is the equivalent of realizing that the night always alternates between white and black squares. Uniting them into the electromagnetic field is akin to discovering that's because the night always moves in an L shape. You've reached a deeper, more comprehensive understanding of the rules. And the quest for similar unifications has kept physicists busy ever since. This was just the tip of a very large scientific iceberg, for Maxwell had another trick up his sleeve. Imagine an electrically charged particle. It generates an electric field around it just like a magnet creates a magnetic field. The particle then starts moving up and down. This changes its electric field, which also then generates a changing magnetic field. According to Maxwell's equations, the constantly changing fields produce ripples that move outwards through the electromagnetic field. Electromagnetic waves. How frequently the particles move up and down dictates how long it takes for the peaks and troughs in the electromagnetic waves to repeat. From his equations, Maxwell calculated the speed of these electromagnetic waves, and the answer he found was remarkable. They move at the speed of light. Surely not a coincidence, Maxwell became convinced that light itself is an electromagnetic wave. Indeed, if true, it would explain how sunlight reaches us despite the sun being 150 million kilometers away. The electromagnetic field would fill the empty space between us, and light could rumble through it like an ocean wave. But how could this be proved definitively? The man with the answer was Heinrich Hertz, now so synonymous with electromagnetic waves that the unit for measuring how many times they repeat in a second is named after him. Hertz first sets up a device capable of producing an electric spark. Then he readies a receiver 15 meters away. When the generator sparks, another spark soon follows in the receiver. To prove that this is caused by an invisible wave traveling between the two devices, Hertz puts a mirror between them. He has to move the receiver in order to get it to spark again because the mirror reflects the wave onto a new path. He's even able to measure the speed of the wave, which turns out to be the speed of light. Hertz has discovered radio waves. Maxwell is vindicated. The rules of the game updated definitively. Light was an electromagnetic wave. And yet, something didn't quite fit. Light was only an electromagnetic wave sometimes. Remarkably, the very same experiment that provided evidence for light as an electromagnetic wave would ultimately show it to be something else entirely, a particle. Hertz noticed that the spark at the receiver was brighter when exposed to ultraviolet light. Later, experiments by other scientists, including Philipp von Leonard, showed that electrons are expelled as a metal absorbs light, which is what brightened Hertz's spark. Brighter light has higher waves, so they should have dislodged more electrons as they crashed into the metal. Yet von Leonard found that it was light waves that repeat more often, those with a higher frequency and not intensity that liberated more electrons. This became known as the photoelectric effect, and would herald perhaps the biggest revolution in the history of science. An explanation would soon follow from none other than Albert Einstein. Despite being famous for his theories of relativity, it was this work on the photoelectric effect that would land him the Nobel Prize. For Einstein argued that light isn't a continuous wave at all, but a series of particles fired out like bullets. Particles that today we call photons. How much energy each photon has depends on the light's frequency, and only photons with high frequencies have enough energy to dislodge an electron. It's similar to a boxing match. Lots of continuous, low-energy punches do little. One sizable knockout blow is all it takes. This was a truly bizarre discovery, and one that would force physicists to concede that their entire chess game was hideously outdated. Almost without exception, every rule would need to be rewritten, complete with startling revelations about the true nature of our reality, and even ourselves. By the end of the thread that Faraday started pulling in 1846, we would find ourselves living in a totally different universe. But to start with, to begin unfolding the rules of this new game, physicists would have to figure out this simple mystery. Why does light come in packets with set sizes? We are trying to prove ourselves wrong as quickly as possible, because only in that way can we find progress. As night falls, Dotonbori ignites into a riot for the senses. The smell of Japanese street food wafts through the air as throngs of people bustle noisily between the crowded Osakan alleyways. But it is the kaleidoscope of color that hits you most. Everywhere you look, neon signs flood the streets with light, advertising king crab, octopus balls, and revolving sushi restaurants. And deep within these famous neon signs, there's an equally frantic hive of activity unfolding. Instead of people scurrying about, tiny subatomic particles called electrons dart this way and that. Without them, the streets of Dotonbori would be dark. They are also the key to understanding photons. Let's journey inside one of Dotonbori's red neon signs, which are filled with hydrogen gas. To reach the individual atoms of hydrogen, we have to zoom in an incredibly long way. A hydrogen atom is almost unfathomably small, around 83 million times narrower than one of your fingernails. If you were to shrink the Earth by the same amount, you could hold the planet in the palm of your hand. Hydrogen is the simplest atom in the universe, made of just two particles, a positively charged proton in the center with a negatively charged electron whizzing around it. Although far from a perfect analogy, it's similar to the Hitomi satellite orbiting the Earth. Indeed, this is how Danish physicist Niels Bohr pictured the hydrogen atom in 1913, in what has become known as the Bohr model. However, Bohr argued that the electron cannot inhabit just any orbit around the proton. Instead, electron orbits are like the food served in the Dotonbori streets. You can't buy a portion in any size you like. You have to choose between set predetermined quantities such as small, medium, or large. Anything in between simply doesn't exist. In the Bohr model, electron orbits are similarly quantized, meaning only certain restricted quantities, or sizes, are allowed. These permitted orbits are called energy levels, and they are the secret behind Dotonbori's cacophony of color. If you pass an electric current through a gas, then you give its electrons an energy boost, which they use to jump up to a higher energy level. When they fall back down again, the energy they lose is spat out in the form of a photon. The energy of the photon is equal to the size of the gap between the energy levels. In turn, this governs the color of the light we see. Red light has the least energy, violet light the most. If all orbits were possible, then we'd only see white light, as all the different colors from the myriad transitions blended together. Yet that is not what we see. If you take the light from glowing hydrogen gas and pass it through a device similar to a prism, then you reveal hydrogen's spectrum. The visible part of this spectrum consists of just 4 colored lines painted on a sea of black. These lines come from photons emitted when electrons drop down to the second energy level from the 6th, 5th, 4th, and 3rd energy levels, respectively. The blackness between the lines is a barren wasteland. It's devoid of light because the electron transitions needed to illuminate it simply don't exist. This pattern is the calling card of the quantum atom. But of the 4 lines, the red one on the far right, known as H-alpha, is significantly brighter than its neighbours. It easily drowns out the other 3, and so the streets of Dotonbori are drenched in red. So far, so good. Not simple, but at least rational. By the 1920s, many of history's greatest physicists, from Max Planck to Einstein to Bohr, had worked on this model of the atom, the result of following the implications of Einstein's photoelectric effect to their logical end. But of course, in Feynman's cosmic chess match, there is always some tiny, obscure move that blows a gaping hole in your theory. One innocuous observation that makes you realize everything isn't quite as it seems. And this particular crack was especially minuscule. If you look carefully at the H-alpha line, you'll see that it isn't 1 line at all, but 2. A doublet. These lines are almost imperceptibly close together, separated by a distance 250,000 times finer than a strand of spider's silk. Physicists call this fine structure, and the Bohr model cannot explain it. Fine structure is itself the equivalent of a big neon sign, flashing with a warning. Theory incomplete. Once again, physicists were forced to return to the drawing board. And today, the solution to the fine structure riddle lies on the other side of the world, in a place as popular with tourists as the street food stalls of Dotonbori, Westminster Abbey. With its imposing towers, Westminster Abbey is one of the jewels in London's crown. Kings and queens have been coronated within its walls for almost 1,000 years. It's also the burial place of many a British icon, from Dickens and Darwin to Kipling and Newton. And on the floor of the Abbey, close to the monument to Newton, a plaque commemorates the life of arguably the greatest English physicist since Newton himself, Paul Adrien Maurice Dirac. Engraved on the plaque is the equation that not only represents the crescendo of Dirac's genius, but one that also resolves the fine structure problem and explains why the H-alpha line is a doublet. The secret is a murky and mysterious property of electrons called spin. We know that when an electrically charged particle moves, it produces a magnetic field. However, experiments show that electrons are actually producing 2 separate magnetic fields, and so they must be moving in 2 different ways. An electron orbits around the atom, but it is also said to be spinning. So, in a way, an electron is similar to the Earth, which both spins on its axis and orbits around the Sun. Except, not quite. For in the case of electrons, spin is just an analogy. They would have to be spinning faster than the speed of light to account for their observed behavior. Nonetheless, physicists still use the word spin to refer to the source of the electron's second magnetic field, and fine structure results from these 2 magnetic fields interacting with each other. Like electron orbits and Dotonbori street food, spin is also quantized. Only certain quantities are allowed. The spin of the electron is 1/2. But this can be either positive or negative, so an electron can exist in one of 2 spin states. Up, where its spin is +1/2, and down, where its spin is -1/2. A spin-up electron creates a magnetic field that adds to the magnetic field generated by its orbital motion, boosting the electron up to a slightly higher energy level. The magnetic field created by a spin-down electron works against the orbital magnetic field, relegating the electron to a very slightly lower energy level. And so the 2 closely spaced H-alpha lines in the hydrogen spectrum are produced by electrons dropping down from these marginally different energy levels. Dirac's brilliance was to bring together several breakthroughs in early 20th century physics in order to explain the weirdness of spin. In 1926, Erwin Schrödinger published his famous Schrödinger equation. Just as a light can act as both a particle and a wave, so can electrons. The Schrödinger equation describes the behavior of these electron waves. Dirac also folded in Einstein's special theory of relativity, which describes how objects behave when they move at high speeds. The result? When Dirac published his own equation in 1928, the one engraved on the plaque in Westminster Abbey, it showed that spin becomes an inevitable property of the electron once you treat it as a relativistic quantum wave. The Bohr model, that describes electrons as like orbiting planets, is consigned to the growing scrap heap of theories physicists have been forced to discard. Atoms are actually made of waves and particles at the same time. The fine structure crack had opened up and consumed the atom whole. But the best scientific theories don't just explain something we already know, they also predict something that we don't. The Dirac equation works whether or not the particles it's describing have positive or negative energy. So Dirac predicted the existence of a particle identical to the electron, but with the opposite electric charge. A particle of antimatter. And just 4 years after Dirac published his equation, the positron was indeed found by Carl Anderson. Compared to the Bohr model, the Dirac equation was certainly a more comprehensive set of rules for how the game of subatomic chess works. But by this point, physicists had understandably become wary of closing the rulebook. And they were right not to. For as they would soon discover, there were yet 2 more minuscule moves in a strange corner of the board that were not covered by Dirac's rules. And in an odd historical coincidence, both were announced at the very same conference in 1947. During the Second World War, many of the leading lights in physics were repurposed to develop militarily useful technology such as radar and atomic bombs. The Shelter Island Conference, held near Long Island in New York, was a chance to refocus on compiling the ultimate rulebook of the universe. The wonderfully named Polycarp Kusch announced his measurements of a property of the electron called its magnetic dipole moment. His answer disagreed with a prediction by Dirac, suggesting that there was still something far deeper and more mysterious at play. And so to explain this, let's return to our bar magnet. It has 2 poles, north and south, making it a dipole. If you place the bar magnet inside another magnetic field, then it will try to align with that field, like a compass needle swinging to point north. The magnetic dipole moment is a measure of the strength of this interaction. The spin of an electron generates a magnetic field, and so it is like a tiny dipole magnet. But the question is, how strong is its magnetic dipole moment? If you don't treat an electron as a quantum particle and assume that it is a small sphere that's actually rotating, you get the wrong answer. The real value of the magnetic dipole moment measured by Kusch is about twice as big. This difference between the quantum and non-quantum answers is called the G-factor. The Dirac equation correctly treats the electron as a quantum object, and it predicts that the G-factor should be exactly 2. However, Kusch's measurements said otherwise. The answer he gets is 2.00238. This seemingly trivial difference became known as the electron's anomalous magnetic dipole moment. It was yet another neon sign illuminating our ignorance, an unexplained gambit in the chess game of the gods. But that was not the biggest shock at Shelter Island. The war had seen huge strides forward in microwave technology, and in his post-war experiments, Willis Lamb had seen hydrogen atoms spitting out microwave photons. Photons that simply shouldn't exist. According to the Dirac equation, 2 of the energy levels within the hydrogen atom should coincide. Instead, Lamb realized that they diverge by just 1 part in a million. When electrons make the transition between them, they produce the microwave photons Lamb saw. This unexpected energy level split became known as the Lamb shift. Lamb would later reflect that it was the smallest of measurements with the biggest of ramifications. Cush and Lamb's work would not only land them a share of the 1955 Nobel Prize, it would press physicists into extending Dirac's equation into what would become the most accurate and exquisitely tested theory in the history of physics. It would unite all we knew about the electromagnetic field and the quantum atom together into a single theory. But with this realization, we'd be forced to accept a truly bizarre new reality. Quantum mechanics describes nature as absurd from the point of view of common sense, and yet it fully agrees with experiment. So I hope you can accept nature as she is. Absurd. For the physicist André Geim, it was just another Friday night in the lab. For the frog, it must have felt like it had been transported into orbit. It hovers in mid-air, spinning and flipping like an astronaut doing somersaults. Geim dedicates 10% of his time to these seemingly outlandish experiments. Along with the frog, Geim and his team would levitate plants, fish, and even a mouse using strong magnets. His efforts would win him the Ig Nobel Prize in 2000, a satiric alternative to the Nobel Prize aimed at recognizing unusual or trivial scientific achievements. And yet, despite the whimsical nature of Geim's experiments, you have a lot more in common with his levitating creatures than you may think. It might seem like you are currently touching the chair you're sitting on or the floor you're standing on. But very simply, you aren't. You are instead floating on a cloud of particles. When you walk, you are not in contact with the ground at all. Instead, you are standing on a swarm of subatomic spectres. Blink and you'll miss them, ghost particles that haunt the quantum world. This is the counterintuitive reality of the gods' game of chess. To quote physicist Frank Wilczek, what you see isn't what you get. The fact that we are all levitating like Geim's frog is the only logical way to explain the seemingly tiny inconsistencies seen by Cush and Lamb. The smallest of effects with the profoundest of consequences. It turned out that the Dirac equation failed to account for Cush and Lamb because although it treated the electron as a quantum object, it still described the electromagnetic field in the way that Faraday and Maxwell did back in the 19th century. Instead, the electromagnetic field also needed to be quantized. It had to be treated as a quantum field, with all the mind-bending consequences that would entail. And so along with other physicists, in the years following his breakthrough equation, Dirac began to develop a very bizarre vision for our world. Imagine that the electromagnetic field is represented by a string. Pluck the string and you give it energy to vibrate. Except that if this is a truly quantum field, these vibrations can only come in set, predetermined sizes. If you don't give the field enough energy to reach the smallest possible vibration, then nothing happens. Physicists have a name for the smallest possible vibration of an electromagnetic field: a photon. Photons and electrons therefore aren't particles embedded in a field, they are the field. Photons are vibrations of the electromagnetic field, and an electron is the smallest possible vibration of a separate electron field. These fields are fundamental, fill the universe, and exist whether a vibration, what we call a particle, is there or not. Here's another way to picture it. Imagine that a field is made up of a grid of tiles, each one connected to a spring. Initially, the field is completely stationary, the tiles are all level, and there are no springs bouncing up and down. Yet if you pull up one of the tiles, in effect injecting energy into a small part of the field, you can set one of the springs oscillating up and down. This localized vibration of a field is what we see as a particle. Crucially though, the spring has some resistance. If you don't pull on the tile hard enough, then it won't budge. In other words, there's a minimum amount of energy required to create a particle. You can increase the size of the oscillation by injecting more energy, but in the case of quantum fields, only vibrations of set, predetermined sizes are allowed. Hence why electrons need a certain amount of energy to jump to a higher orbital. Vibrations within quantum fields only come in multiples of the smallest possible vibration. Anything in between is forbidden. As well as this, vibrations in one quantum field can be transferred to another. When physicists say that an electron drops down an energy level, like in the Dotonbori lights, what they really mean is that a localized vibration in the electron field vibrates less. This lost energy is transferred to the electromagnetic field, creating a localized vibration there that we call a photon. Picturing this process using particles is perhaps easier to wrap your head around, but there aren't actually any particles involved at all. It is all just vibrating fields interacting with one another. The idea of particles as mere vibrations is known as quantum field theory, and it also explains the antimatter first predicted by Dirac. An electron is a vibration of the electron field, but its antimatter partner, the positron, is a vibration of the same field in the opposite direction. The equivalent of pulling the tile down instead of up. That's why the two so-called particles have identical properties save for their opposite electric charges. When an electron and a positron meet, their oscillations cancel each other out and the electron field stops vibrating. Their energy is transferred to the electromagnetic field, which vibrates to create two photons. This is called annihilation. The reverse can also happen when a photon's energy is transferred to the electron field to create an electron-positron pair. Unsurprisingly, this process is called pair production. It was Dirac who first came up with the name for this theory of how light and matter interact. He called it quantum electrodynamics, or QED. But how do these quantum fields explain Cauchy's anomalous measurement of the electron's magnetic dipole moment and the Lamb shift? And where do the ghostly particles you're levitating on fit in? The answer would come from physicist Julian Schwinger. Born in New York in 1918, Schwinger fell in love with physics during a lecture by Dirac that he attended when he was just 14 years old. By 16, he'd enrolled as an undergraduate at the City College of New York. Clearly a precocious talent, legendary physicist Hans Bethe said of a 17-year-old Schwinger, "His knowledge of quantum electrodynamics is certainly equal to my own, and I could hardly understand how he could acquire that knowledge in less than 2 years." If QED explains the interaction between light and electrons through quantum fields, those fields must also be subject to all the rules of the counterintuitive quantum world. And that includes the Heisenberg uncertainty principle. The Heisenberg uncertainty principle is a loan agreement with the universe. It says that you can borrow energy from empty space as long as you pay it back again within a certain amount of time. The more energy you borrow, the quicker you have to pay it back. This borrowed energy can pull up a tile and vibrate a quantum field to create a particle, but then that vibration disappears again once the energy debt is repaid. Physicists refer to these ghostly vibrations as virtual particles. It means that an electron is never really alone. The electromagnetic field around it is constantly vibrating with borrowed energy, creating a swarm of virtual photons that flit in and out of existence. Sometimes the virtual photons exist for long enough that they undergo pair production to produce virtual electron-positron pairs, but they also soon disappear. Before they vanish, these poltergeist particles buffet the real electron into a slightly different energy level inside the hydrogen atom, which is exactly what Willis Lamb had observed. They also influence the electron's magnetic interactions, explaining why Cauchy's measured G-factor was slightly higher than in the Dirac equation, which doesn't treat the electromagnetic field as a quantum field. In the years since, physicists have measured the magnetic dipole moment of the electron to an unbelievable level of accuracy. According to QED, the electron G-factor should have a value of 2.0023193043552. In February 2023, physicists announced the most precise measurement of the electron G-factor ever made. Their answer? 2.0023193043643612. Correct to about 1 part in a trillion, making QED the most accurately tested theory in the history of physics. It's the same as measuring the distance to the moon to within less than the width of a human hair. Without the presence of virtual particles, the G-factor would be exactly 2. They may come and go, but their ghostly influence leaves an imprint on the real world that is there for all to see. It's as if a piece on the chessboard has moved without anyone ever actually touching it. Our rulebook has to include these phantom moves, too. The fleeting existence of virtual particles has profound implications for the way we explain the world around us, starting with how magnets work. Out goes Faraday's 19th century idea of field lines, and in comes the exchange of virtual photons. Imagine that you and a friend are each standing on a boat. If you throw balls back and forth between you, the boats will move apart. In the same way, two matching magnetic poles move apart by exchanging virtual photons. If the poles are opposites, then they attract each other also by exchanging virtual photons, but this time in a way that's a bit like throwing boomerangs between the boats instead of balls. In a similar fashion, it's virtual photons that make up the cloud upon which you are currently levitating, like Guy's frog. Electrons orbit so far out from the nucleus that atoms are mostly empty space. You should fall straight through the chair or the floor as atoms pass through atoms unhindered. That you don't is only because the electrons in the floor or the chair and the electrons in you are constantly exchanging virtual photons, pushing each other apart like two magnetic north poles without ever actually touching. You are forever floating on the most ephemeral of quantum clouds. Physicists have juggled with the implications of virtual particles ever since Heisenberg introduced his uncertainty principle in 1927. Within 2 years, Schwinger's PhD supervisor and later father of the atomic bomb, Robert Oppenheimer, realized they presented a big problem for the success of QED. When he used an early version of the theory to add up the contribution of the multitudes of virtual particles swarming around an electron, it suggested that the energy an electron emits as it changes energy levels is infinite. QED could seemingly not explain something as basic as the spectral lines of hydrogen so beautifully explained by both Bohr and Dirac. Calculations of the mass and charge of the electron also gave infinity as the answer. Infinity isn't even a number, but instead the notion or idea of endlessness. When it crops up in physics, it is another big neon sign, imploring physicists to try harder. This infinity problem meant that QED looked dead on arrival, yet another false dawn. But this was not to be the end for the theory, for it was to eventually be salvaged by Schwinger and others in the 1940s, using an incredibly powerful theoretical technique. The Lamb shift and the electron's anomalous magnetic dipole moment had shown physicists that the effect of virtual particles is finite and not infinite. The influence they have is measurable. Theorists didn't have to fully understand why QED initially gave the wrong answer. All they needed to do was tweak their equations in such a way that they produced the values measured by Lamb and Cush. Altering a theory in this way to vanquish the unwanted infinities is a mathematical conjuring act called renormalization, and scientists use the technique to this day to blast through seemingly impenetrable problems. And so, these two tiny effects in a shadowy corner of the cosmic chessboard became doubly important. Not only did they show that Dirac's initial set of rules was incomplete, they also helped to improve the set of rules that replaced it. The infinities were overcome, and suddenly QED was a working theory capable of predicting real outcomes with startling precision. The first true quantum field theory. Schwinger would go on to share the 1965 Nobel Prize with Richard Feynman and Shinichiro Tominaga, the other Grand Masters who also figured out the route to renormalization. But the staggering success of QED set physicists wondering. If the electromagnetic force between magnets could be so exquisitely explained as nothing more than ripples in a quantum field, what about nature's other forces? How far could they go? How much of reality could be explained as mere vibrations in fields? Because atomic behavior is so unlike ordinary experience, it's very difficult to get used to, and it appears peculiar and mysterious to everyone, both to the novice and the experienced physicist. The trail of people marching out of the wooden huts and over the Chilkoot Pass resembles an army of ants. The boot prints left by their frostbitten feet snake for miles around the mountains. 100,000 eager explorers have descended on Canada's Yukon River and the surrounding Klondike region, a frenzy sparked by the discovery of gold. But most never even make it to the gold fields, forced to turn back empty-handed by the elements, or worse, killed by infectious diseases, avalanches, or assault. Today, the Klondike is far more serene than it was during the gold rush at the end of the 19th century, but the precious metal is still mined here. And in 2022, miners unearthed a very different kind of treasure buried in the permafrost. A perfectly preserved woolly mammoth. Scientists estimate that the mammoth lived around 30,000 years ago. But how do they know? It is the answer to that question that provides the key to the next set of quantum rules. For ever since the mammoth died, a subatomic clock has been silently ticking away inside it, a timepiece based on atoms of carbon-14. The nucleus of a carbon-14 atom contains 6 protons and 8 particles called neutrons. Occasionally, one of the neutrons spontaneously shapeshifts into a proton. As it's the number of protons that distinguishes different chemical elements from one another, it is no longer an atom of carbon. It is now an atom of nitrogen, with 7 protons and 7 neutrons. This random process is called radioactive decay, and the more carbon atoms that have changed to nitrogen, the older the specimen must be. But this type of radioactive decay is governed by an entirely different force than the one that controls magnets and electrons, a force that appears to be considerably more feeble, hence its name, the weak force. And the story of how physicists came to truly understand the rules of the weak force and its various moves on the board began in the Bronx High School of Science in New York City, way back in 1950. That year, the graduating class at Bronx High contained not 1, but 2 future Nobel Prize winners. Not only that, they would win the same prize in the same year for contributions to the very same theory, despite working on it separately. They were Sheldon Glashow and Steven Weinberg. Both Glashow and Weinberg ended up at Cornell University after Weinberg's father drove them round to look at various colleges. After graduating, Glashow moved to Harvard to complete a PhD under the watchful eye of Julian Schwinger. Having renormalized quantum electrodynamics, Schwinger set Glashow thinking about whether the weak force could also be explained using a quantum field. We've already seen how the electromagnetic force is carried by virtual photons that flit between the poles of a magnet and even between your feet and the floor. Physicists call such force-carrying particles bosons. But which boson is responsible for ferrying the weak force? The answer lies partly in the decay of carbon-14 into nitrogen-14 used in carbon dating. The weak force turns an electrically neutral neutron into a positively charged proton, along with an electron and a particle called an electron antineutrino. This process is called beta-minus decay, but it can happen the other way round too. During beta-plus decay, a proton changes into a neutron plus a positron and an electron neutrino. In other words, the weak force is able to change a particle's electric charge. A photon, the boson of the electromagnetic force, does not have this power. When an electron absorbs a photon, it stays negatively charged, so the weak force must have at least two bosons, one involved in changing neutral to positive and another in changing positive to neutral. It was Weinberg who chose the letter W for weak, giving us the W+ and W- bosons. And so physicists, including Schwinger and Glashow, attempted to explain these weak force interactions using a quantum field theory, just as they had done for the electromagnetic force. These W bosons were reasoned to be the minimal possible vibrations of the W field, just as the photon is for the electromagnetic field. Just like the photons flying between magnets, the W+ and W- bosons involved in the two forms of beta decay are also virtual, poltergeist particles that disrupt reality before quickly disappearing back into the quantum shadows. In this way, we date archaeological treasures with the help of particles that aren't really there. Except turning the weak force into a fully fledged quantum field theory was proving more than a little tricky. For one thing, the mathematics predicted 3 bosons, not 2. And so Glashow suggests the existence of a new, electrically neutral boson instead, Z, for the fact it has 0 charge. So the weak force is carried by 3 bosons, W+, W-, and Z. They are the product of 2 different quantum fields, one for the 2 W's and one for the Z. Progress is made, but there is a bigger problem. This trio of bosons has mass. They must do, because the distance over which the weak force operates, what physicists refer to as its range, is tiny, just 1/100th of a trillionth of a millimeter. This behavior suggests that virtual bosons responsible for carrying the weak force disappear incredibly quickly, before they can get very far. The time it takes for half of them to disappear, known as their half-life, is just 3 10-septillionths of a second. There are more of those half-lives in a single second than there have been seconds since the Big Bang some 13.8 billion years ago. And this is why it's called the weak force. It's not that it's inherently weak when it does act. Instead, the weak force rarely acts at all because the virtual bosons that carry it disappear so quickly. The reason that a very short lifetime means that weak bosons have a significant amount of mass is again the Heisenberg uncertainty principle, the lone agreement with nature that is responsible for virtual particles in the first place. Remember, you can borrow a little energy for a long time or a lot of energy for a little time. The incredibly short lives of weak bosons suggest they must have borrowed a lot of energy. According to Einstein's famous equation E = mc², high energy also means high mass. And so the weak bosons are each around 100 times heavier than a proton, or 160,000 times heavier than an electron. But this threw a spanner in the works. Weak bosons having mass meant that renormalization, the fabulous trick that physicists use to vanquish infinities from quantum electrodynamics, only worked for massless bosons, like photons. The infinities were still all too present if you wanted to treat the weak force as a quantum field and its bosons as its vibrations. And so it was Glashow's old school friend, Steven Weinberg, who helped figure out the way through the quagmire with a remarkable thought. Yet another condensing of the rules. What if the electromagnetic field and the weak field were once one and the same? While physicists had been busy trying to write the quantum rulebook of the gods' chess game, astronomers had realized that the universe began as an incredibly small, hot point known as the Big Bang. Together, physicists and astronomers began to explore the possibility that there was originally one so-called electro-weak field, which separated out into the electromagnetic and weak fields as the universe expanded and cooled. If this electro-weak field had massless bosons before the separation, then it could be treated as a quantum field without being plagued by the infinity problem. The issue then became how to go from one field with massless bosons to 2 separate fields, only one of which has bosons with mass. And this is how Weinberg got it to work. Let's say the electro-weak field had 4 massless bosons. We'll call them W1, W2, W3, and B. Another field also needs to have existed, which we'll call the H field. The H field is initially dormant, but spontaneously activates, bringing its own 4 bosons into play. They are called H+, H-, H0, and little h. The activation of the H field breaks the underlying symmetry of the electroweak field, and it separates out into the weak and electromagnetic fields. The H bosons also have the power to give other bosons mass. The W1 and H+ bosons combine into the W+, and the W2 combines with the H- into the W-. W3 and B merge to create 2 new massless bosons. One of them combines with H0 to make the Z boson, and the other one never combines with an H boson, and so it never gains mass. It is the massless photon. By now there's a chance you may have guessed what all the H's stand for. Higgs. And therein lies the beauty of this electroweak theory, sometimes called quantum flavor dynamics, or QFD. Not only does it explain why the weak bosons have mass and the photon does not, it also makes a big prediction. One of the 4 original H bosons, little h, should have survived this convoluted process unscathed. And so began the search for perhaps the most lauded particle in physics history, the Higgs boson. Schoolmates Glashow and Weinberg shared the 1979 Nobel Prize in Physics, alongside Pakistani physicist Abdus Salam, for their work on this electroweak unification. Suddenly, we didn't need one set of rules to explain the electromagnetic field and a separate set to explain the weak field. The rules of the electroweak field sufficed. In much the same way James Clerk Maxwell had united the electric and magnetic fields into a single electromagnetic field in the first place. 2 seemingly totally different rules blended into one underlying framework. But this was not the end. For while theoretical physicists had been mapping all of this out, experimental physicists had continued to probe deeper and deeper inside the atom. And in doing so, had found a zoo of particles and a whole new layer to reality. The protons and neutrons within atoms also turned out to be made of smaller particles, governed by yet another fundamental force. Could this also be explained with quantum fields? Was the very matter that made up atoms simply vibrations, too? You can't say A is made of B or vice versa. All mass is interaction. Your heart is pounding in your chest as the deafening wind roars past your face. As you hurtle towards the ground, a heady dose of adrenaline courses through your veins. Then, at the very last second, the bungee cord snaps you back from the brink of oblivion. This white-knuckle ride is similar to the experience of subatomic particles called quarks. They make up the protons and neutrons found in the hearts of atoms. Except, if they try to free themselves from these particles, they are always wrenched back in. Independently proposed by Murray Gell-Mann and George Zweig in 1964, protons and neutrons are made of 2 different types of these quarks: up and down. Inside a proton, you'll find 2 up quarks and 1 down quark. The up quarks each carry an electric charge of +2/3, and the down quark an electric charge of -1/3. So the proton has an overall positive electric charge. A neutron has only 1 up quark, the charge of which is cancelled out to neutral by its 2 down quarks. And so there is no such thing as the proton or neutron field. Instead, there is only the up quark field and the down quark field. Up and down quarks are the minimal possible vibrations of these quantum fields. The objects we call protons and neutrons are actually 2 different quantum fields vibrating in tandem. The very atoms that make up our reality are nothing but interconnected vibrating fields. However, understanding protons and neutrons in terms of quarks did present physicists with some challenges. Firstly, like electrical charges repel each other, just as like magnetic poles do. So why don't the two positively charged up quarks in the proton push apart, or the negatively charged down quarks in the neutron? Physicists reasoned that there must be another attractive force at play, mightier than the electromagnetic force. The strong force. Like the electromagnetic force, the strong force is also carried by massless bosons, this time called gluons, because it's only by exchanging them that quarks stay glued together. Gluons are the minimal possible vibrations of the gluon field. But of course, as we have seen time and time again, there was still one small issue that would bring this new theory to breaking point. For in 1964, the same year quarks were proposed, physicists had discovered a truly baffling particle, the omega minus particle. The quark zoo is home to beasts more exotic than up and down quarks. There are also flavors of quark called strange, charm, top, and bottom. Each one is the minimum possible vibration of its own quantum field, meaning there are 6 quark fields in total. The problem was that the troublesome omega minus particle was made up of 3 strange quarks, and this seemed to break a sacrosanct law of quantum physics known as the Pauli exclusion principle. We've already seen that all electrons have a property called spin, with a value equal to a half. Likewise, quarks also have spin equal to a half. The Pauli exclusion principle states that it's impossible for 2 spin-half particles to exist in exactly the same quantum state. But what about the 3 strange quarks in the omega minus particle? Let's say one of them has a spin of plus 1/2, and a second has a spin of minus 1/2. What about the third? It doesn't matter if its spin is positive or negative, either way it will still be in exactly the same state as one of its neighbors, in direct violation of the Pauli exclusion principle. The omega minus particle was another big neon sign, another crack in a theory that slowly revealed a whole new layer of ideas. It told physicists that quarks must be ruled by some extra property that distinguishes them instead, something electrons don't have. Color. Color is the charge associated with the strong force, just as electric charge is associated with the electromagnetic. A quark can have one of 3 color charges, called red, blue, and green. Quarks don't actually have different hues though. Like spin, color is just an analogy. Using colors to name the 3 strong force charges was the brainchild of physicist Wally Greenberg, who took inspiration from someone we've met before, James Clerk Maxwell. In the 1860s, Maxwell demonstrated that combining red, blue, and green light creates white light. In other words, all color disappears when the 3 are mixed. Equally, when one of each red, blue, and green color charge combine, they create a particle with a neutral color charge. Protons, neutrons, and omega minus particles don't behave like they have this strong force charge, so they must be color neutral. That means they are made of 1 red quark, 1 blue quark, and 1 green quark. No 2 quarks are exactly the same, and the Pauli exclusion principle is saved. And the fact that physicists use colors to name strong force charges gives the quantum field theory of the strong force its name: quantum chromodynamics, or QCD. Quantum electrodynamics has 1 boson, the photon, and quantum flavor dynamics added a trio of weak bosons, the W+, W-, and Z. However, QCD says that the strong force is carried by a total of 8 bosons, an octet of multicolored gluons. Here's why. Like all force-carrying particles, the exchanged gluons that stick quarks together are virtual children of the Heisenberg uncertainty principle. We've already seen how virtual photons can turn into virtual particle-antiparticle pairs that nudge real electrons. Similarly, a virtual gluon can turn into a virtual quark-antiquark pair. If quarks carry red, blue, and green charges, then antiquarks carry anti-red, anti-blue, and anti-green charges. So the strong charge on a gluon is a mixture of a color and an anti-color. When a quark absorbs a gluon containing a particular color charge, it changes to that color. So a blue quark absorbing a gluon containing red charge turns red. Conversely, when a quark emits a gluon containing an anti-color, it changes to that color. So a green quark spitting out a gluon containing anti-blue charge turns blue. This makes it impossible for a gluon to be made of a color and its own anticolor. Let's say a red quark could emit blue anti-blue gluons. This would both turn itself blue and turn the green quark blue when it absorbs them. You'd have two blue quarks inside the same particle. There would no longer be one of each color to mix together to be color neutral, so the proton or neutron would exhibit some overall color charge, which they never do. There are 6 ways to pair off 3 colors so that you never get matching colors in the same pair. That's 6 gluons, but what about the other 2? The quantum world being the weird and counterintuitive realm that it is, there are actually 2 complicated ways for each quark or antiquark to be a mix of colors while still leading to a neutral color charge. This makes protons and neutrons like miniature universes, relentless hives of activity, constantly shifting kaleidoscopes of color charges, with a rainbow of virtual gluons, quarks, and antiquarks flitting here and there. These virtual particles are so abundant that they make up 99% of the mass of a proton or neutron. The real quarks they are buzzing between contribute just 1%. The very particles that make up every atom in your body are mostly made of things that aren't really there. You can think of the constant back and forth of gluons between quarks as like a bungee cord between them. Physicists call it a QCD string. Try and pull a quark out of a proton and the bungee cord tenses and wrenches the quark back in, like our bungee jumper earlier. It is possible to put in enough energy to snap the bungee cord completely, yet this still doesn't set the quark free. Instead, the energy is converted into a quark-antiquark pair called a meson. The meson escapes and carries away the energy, but the quark remains trapped. Collisions within particle accelerators are so energetic that the bungee cord is broken multiple times, spitting out an abundance of mesons. They form jets, and it's these jets that particle physicists pore over for hints about what has happened. Only then do signs of color emerge, as it's transferred from particle to particle. Yet these virtual mesons have an even more important role to play. In most atomic nuclei, there are multiple protons, each with a positive electric charge. Like all electrically charged particles, they are exchanging virtual photons, which acts to push them apart. Yet this is trumped by the virtual mesons they are also exchanging, which keeps them glued together. Physicists call this the strong nuclear force, to distinguish it from the strong force that binds quarks. They can also stick a proton and a neutron together. Every element in the periodic table heavier than hydrogen would be impossible without these virtual mesons. No stars, no planets, no life. So not only are the particles you're made of mostly comprised of things that don't really exist, those things are also held together by things that don't really exist either. The more we figure out the rules of quantum chess, the stranger and stranger they become. In 2004, David Gross, David Politzer, and Frank Wilczek shared the Nobel Prize in Physics for their work on quantum chromodynamics. They showed that the strong force and all its myriad color interactions can be described using a renormalizable quantum field theory, just as the electromagnetic and weak forces can. That quarks, gluons, and mesons are all just ghostly vibrations in quantum fields. This means that currently everything in the atomic world can be explained using just 2 theories. The electroweak theory, which includes quantum flavor dynamics and quantum electrodynamics within it, and quantum chromodynamics. Together, they make up the Standard Model of particle physics. The Standard Model describes a total of 17 vibrating, overlapping quantum fields. occupying every part of space. There are 4 fields associated with the force-carrying bosons: the photon, the W bosons, the Z boson, and the gluon. Then 6 quark fields, 1 for each flavor. There are also 6 fields known as lepton fields. Leptons are particles not affected by the strong force. That includes the electron field, and 2 fields associated with particles called the muon and the tau, plus a trio of fields for the 3 different kinds of neutrino. That's a total of 16. But what about the 17th field? That is the much-lauded Higgs field, vibrations of which we know as the Higgs boson. That boson was discovered in the summer of 2012 at CERN's Large Hadron Collider, a cavernous cathedral built to prize answers from the Standard Model. The discovery of the Higgs was a ringing endorsement of the Standard Model as the most comprehensive rulebook for the gods chess game ever compiled. It successfully explains how all subatomic particles and 3 of the fundamental forces can be described as mere vibrations across its 17 different quantum fields. Waves and particles, mass and energy, light, air, earth, and the matter that makes up me and you. Almost everything could be reduced to vibrations in vast, universe-spanning, interacting quantum fields. Almost. Because for all of the Standard Model's successes, there is still one thing left. One rule that just doesn't fit. Gravity. If a law does not work even in one place where it ought to, it is just wrong. Clad in gleaming white spacesuits, a team of astronauts checks the last of the rivets and bolts. An armada of robotic spacecraft sets to work, cooling the magnets to a temperature lower than even empty space itself. After centuries of toil, the much-anticipated machine is finally ready. To call it vast would be an understatement. It encircles the Sun like the path of a planet orbiting far beyond any of the actual planets of the solar system, its total length stretching to some 37 billion kilometers. And physicists are about to send subatomic particles in opposite directions around this superring at close to the speed of light. Even though the particles are traveling at almost 300,000 kilometers per second, physicists won't see the first collisions for a day and a half. Even then, they'll need the particles to make millions of laps before they have enough data to piece together what's going on. They will need to be patient. It won't be for generations until they finally see the results. The particles have to stream past the robots mining the space rocks in the asteroid belt for the materials required to make machines like this one, by the towering cities of New York and New Delhi on the dusty Martian surface, and beyond the sprawling solar farms on Mercury that are powering humanity's growing presence across the solar system. This mega machine is the ultimate microscope, allowing physicists to zoom in and see reality at the smallest scales. With its incredibly high energies, this Ultra Hadron Collider is probing the so-called Planck length, which is just 62 nonillionths of a millimeter across. There are around 1 billion times more Planck lengths in a single millimeter than there are stars in the entire observable universe. It is only by exploring the universe in such minute detail that physicists can hunt for proof of what has always eluded them. A theory capable of explaining every phenomenon in the known universe, from the tiniest subatomic particle to the most gargantuan galaxy. A theory that proves, once and for all, that everything, even gravity, can be explained as ripples within quantum fields. A theory of quantum gravity. Such an experiment is clearly a long way off, but it represents the dream scenario for many physicists. Just as the electromagnetic and weak forces were once united into the electroweak force, Physicists suspect the electroweak force was once tangled up with the strong force into a single quantum field. The fact that both have already been successfully described using quantum field theories shows that they are highly compatible. They look to be like two pieces of a locket, naturally fitting together to make a whole. The marriage of the two is known as grand unified theory, and it is an inherently testable idea. For one thing, physicists suspect it could lead to proton decay, where the proton breaks down into lighter particles, and so searches are already underway for proof of this process. Evidence that in turn the gravitational field was once spliced together with the grand unified field into a single quantum field is what our solar system-sized accelerator was looking for. Just as the other three forces have force-carrying bosons, our future physicists were on the hunt for the graviton, the minimum possible vibration of the quantized gravitational field. Yet despite this being a superficially logical extension, such a notion is fundamentally incompatible with the way physicists currently understand gravity. Our best theory of gravity is Albert Einstein's general theory of relativity. It says that the universe is made of a fabric called space-time. If, as Shakespeare wrote, all the world's a stage, then space-time is the stage and quantum fields merely players upon it. The 17 quantum fields of the Standard Model vibrate in space and over time. Space-time is space and time. According to general relativity, mass or energy embedded in space-time creates a depression known as a gravity well. If a second object gets trapped in this gravity well, then it will look like the first object is preventing it from escaping by pulling on it. Isaac Newton thought that this was the attractive force of gravity, but gravity isn't really a force at all. It's just the effect of the curved space-time inside a gravity well. By describing it in this way, general relativity treats gravity very differently to the way quantum field theories explain the other three fundamental forces through the exchange of virtual bosons. In general relativity, there's no bungee cord of virtual gravitons traveling between the Sun and the Earth, and trying to explain gravity through the exchange of virtual gravitons instead is immensely troublesome. For one thing, there's a problem when physicists calculate the chances of a particle emitting or absorbing a graviton. The answer they get is significantly higher than 1. In probability, the likelihood of events is scored on a scale from impossible at 0 to certain at 1. A probability of more than 1 is saying that an event is somehow more certain than certain. Said another way, there's more than a 100% chance of it happening. This is clearly nonsense, and yet another red neon warning sign. But there's an even bigger issue. Let's say the Sun and the Earth really are exchanging gravitons. Those gravitons have energy, so they would warp space-time, which would lead to more gravitons. They too would warp space-time, leading to yet more gravitons. Very quickly, this spirals out of control and races towards infinity, resulting in the equations blowing up and losing their predictive powers. If this sounds familiar, you're not imagining it. This is exactly the same problem that plagued early versions of quantum electrodynamics. Robert Oppenheimer added up the effect of all the virtual particles swarming around the electron, and he got infinity as the answer. Blushes were only spared because the Lamb shift and Cush's unexpected measurement of the electron's magnetic dipole moment showed physicists how to fudge their equations to produce the right answer through renormalization. But physicists don't yet know how to renormalize quantum gravity and vanquish the infinities. Maybe another tiny gambit will one day blast a hole in either general relativity or the Standard Model, a final move in the centuries-old game of divine chess that physicists have yet to observe. One that would help them to complete the rulebook once and for all. Perhaps it will take a solar system-sized accelerator to find it. But in the meantime, physicists have tried other ways to break the impasse, and the most famous attempt is string theory. String theory says that the particles described as fundamental in the Standard Model, such as quarks and electrons, aren't fundamental at all, but are instead made of tiny vibrating strings. Just as you can play different strings on different musical instruments to produce different notes, so the universe creates the orchestral masterpiece of the standard model by conducting its own string section. Open strings would have the properties of photons and gluons, but a closed string could have all the expected properties of a graviton. Except there are a number of fairly sizable catches. To get rid of the problem of the probabilities adding up to more than one, string theory has to invoke the influence of new particles that no one has ever seen. To vanquish the infinities, you also have to assume that space-time has at least 9 spatial dimensions, perhaps more. As we only see 4 dimensions, 3 of space and 1 of time, the others must be curled up really small and out of sight. Normally, Feynman's chess game gets simpler as successive unifications draw the rules together. String theory, however, seems to make it inherently more complicated, with the need for a slew of new playing pieces. What makes it even more complex is that there are countless versions of string theory, and string theorists aren't sure which set of rules to use to make testable predictions to see if it's correct. So what other options are there? When pressed, many physicists will concede that general relativity seems more likely to crack first. We've seen many times how the discovery of some new gambit forced physicists to throw away an existing non-quantum theory in favor of a new quantum one. Perhaps we haven't seen the thing that breaks general relativity yet because we haven't probed small enough regions of space-time. And this idea is far from new. One man was thinking about it as far back as the 1930s. Born in what is now Ukraine in 1906, Matvei Bronstein's work spanned an impressive gamut of subjects, from semiconductors to quantum electrodynamics and cosmology. But it is his 1935 paper on the problem of quantum gravity for which he is most remembered. Let's say we want to measure a really small region of space-time. Bronstein imagined placing a particle there to help us make the measurement. It's here that the Heisenberg uncertainty principle re-enters our story. We've already encountered the version relating energy borrowed for a certain amount of time, but Bronstein considered another version involving the position of a particle. This version says that as you explore smaller and smaller distances, you need a particle with a higher and higher energy to do so. But Einstein's E equals mc squared tells us that energy means mass. Eventually, there comes a point when the distance you're probing becomes so small that the particle you need creates a gravity well so deep that nothing can escape. And physicists already have a name for an inescapable gravity well: a black hole. Your test particle has created its own black hole, and since you can't see inside a black hole, you can no longer measure the particle. In other words, there's a minimum distance below which it is not possible to measure anything, just like there's a minimum vibration of a quantum field. You've zoomed in and found that space-time doesn't look the same at the smallest scales after all. If true, space-time would not be the smooth and continuous fabric that general relativity describes. Instead, it would come in multiples of the smallest possible size. Bronstein had hit upon another way that space-time could be quantized. However, the bright flame of Bronstein's genius was soon to be extinguished. Just 3 years after the publication of his work, he was executed in a Leningrad prison as part of Joseph Stalin's Great Purge. His wife Lydia was told he'd been sentenced to 10 years of hard labor. He was just 31 years old. But where Bronstein began, others would eventually follow. Today, his work has morphed into the theory of loop quantum gravity. According to this theory, space-time is like a piece of clothing. From a distance, it looks like a smooth fabric, but zoom down far enough and you'll see that it's really made of a network of individual stitches. These are the loops in loop quantum gravity, the threads with which the quantum gravitational field is woven. Each loop is unimaginably tiny. There would be more loops in a cubic centimeter of space than there are cubic centimeters of space in the entire observable universe, somewhere in the region of 10 followed by 99 zeros. Each loop is a quantum of the gravitational field, so loop quantum gravity does away with the need for gravitons and all the problems that come with them. However, so far, like string theory, there is no experimental evidence that loop quantum gravity is the right approach either. And so, perhaps this quest will be passed down to distant generations, who will build particle accelerators the size of the solar system to peer down into the depths of reality. Maybe then, loop quantum gravity or some similar theory will relegate space-time from its role as the stage on which all quantum fields tread the boards to just another quantum field. Then, there would be no stage at all. Our entire reality would be created through quantum field stacked upon quantum field. A universe made of nothing more than ethereal ripples. You've been watching the entire history of the universe. Don't forget to like and subscribe and leave us a comment to tell us what you think. Thanks for watching, and we'll see you next time.